Hey, what's up, guys? So in this lecturette, I'm going to discuss cumulative distribution function, which happens to be a different probability model for discrete random variables and for random variables in general. And along the way, we are also going to discuss some statistical parameters that are typically used to describe probability experiments. And those are expected values, averages, functions of different random variables, and moments and central moments. So let's start with cumulative distribution function. So the cumulative distribution function of a random variable x is also a probability model for that random variable x. Specifically, a cumulative distribution function gives you the probability that random variable capital X is less than or equal to small x. Unlike the probability mass function, which gives you the probability that random variable capital X takes on a very specific value, small x. Cumulative distribution function is represented using capital F, whereas probability mass function is represented using capital P. While working with discrete random variables, mostly we limit ourselves to probability mass functions for calculating different probability events. But sometimes we may want to use cumulative distribution function, specifically if we are interested in finding out the probability that random variable x belongs to a range of values. In such cases, cumulative distribution function is easy to use versus a probability mass function. So let's take a look into what cumulative distribution function really looks like. To develop a cumulative distribution function, consider a PMF or random variable capital X, which is equal to P1 for x is equal to x1, which is equal to P2 for x is equal to x2, it's equal to P3 for x is equal to x3, and it is 0 otherwise. So let's draw a cumulative distribution function graph for this random variable x using the definition that CDF, the cumulative distribution function, gives you the probability that x is less than or equal to small x. Because we are evaluating probability that x is less than or equal to small x, essentially what we need to do is we need to add all the PMF values for those values of x that are less than small x. That's what we need to do. We need to perform an accumulation. Because of this summation term, we are accumulating the probability values, and therefore cumulative in the name cumulative distribution function. So let's draw a CDF chart for this random variable x that has a PMF that looks something like this. So on the x-axis, you will have your random variable capital X, and on the y-axis, you will have f of x. On the far left side, you have negative infinity, and on the far right side, you have positive infinity. Your CDF is going to start always at 0. Your CDF always starts at 0 at negative infinity. The reason being, probability that random variable capital X is less than or equal to negative infinity is actually 0. And this CDF is going to stay at 0 unless it encounters what we call a discontinuity. So x1, x2, x3, they are the points which leads to accumulation in the value of a CDF, because probability that x is equal to x1 is P1. So at that point, we accumulate this value P1 into the running sum of the CDF. So these points, x1, x2, and x3, cause sudden jumps in the values of the CDF, and therefore they are called as discontinuities. So let's draw the CDF for this particular case. So at value x1, this CDF is going to make a jump. Specifically, it's going to jump by an amount which is equal to probability that random variable x is equal to small x. So at this point, the value of the CDF is P1. Then it is going to remain stable until the next point, x2, at which point this CDF is going to jump again. This CDF is again going to jump by an amount equal to the probability of that random variable x takes on x2. So the jump amount is going to be equal to by P2. So now my CDF is at a new value, which is P1 plus P2. This CDF is going to remain constant at the next discontinuity, which is x3, at which time there's going to be another jump. And this jump is also equal to the probability that random variable x is equal to x3, and that is P3. So now the CDF value is new value, which is P1 plus P2 plus P3. And this is the final point, and from this point onwards, the CDF is going to remain stable. There's another important property of the CDF, and that is that at infinity, the value of the CDF is equal to 1. So P1 plus P2 plus P3 should be equal to 1. And that is true because x1, x2, and x3, they constitute the sample space, or they constitute the outcomes in the sample space. So naturally, by adding their probabilities, I should get the value equal to 1. So this is the curve for the CDF of capital X. And I can write this function something like this. F of X is equal to, it's equal to P1 for X greater than equal to X1 but less than X2. It's equal to P1 plus P2 for X greater than or equal to X2 but less than X3. It's equal to 1 for X greater than or equal to X3. So that's the CDF of random variable X, which we have just derived. Now, using this CDF, let's look into some interesting important properties. The very first property is that the value of the CDF at discontinuities is the upper value. By what I mean by that is x1, x2, and x3 are the points where we see sudden jumps in the value of the CDF. When you consider point x2, it is ambiguous as to whether should I consider the value of CDF as this lower point here or this upper point. It's always the upper point. So the value of the CDF at the discontinuity is always the upper point. Some other interesting properties. Your CDF is going to be an increasing function of X, meaning that there's never going to be a dip in your CDF as your X increases. The reason being, since we are accumulating probability values, the running sum has to be always an increasing function of X. It can never ever dip. A decreasing value of a CDF would mean that we have a negative probability value, which never happens. Another important aspect of a CDF is that the value of the CDF at the in-between values is equal to the leftmost value. So for example, if I were to consider a point here, let me call it x2 plus epsilon, the value of the CDF at x2 plus epsilon is going to be the leftmost value, meaning that f of x at x plus epsilon is equal to f of x at x. Specifically, f of x at x2 plus epsilon is equal to f of x at x2 in this particular case. So these are some of the common properties of a CDF. So let's summarize these properties here. So f of x at negative infinity is equal to 0 and f of x at positive infinity is equal to 1, meaning that CDF starts at 0, climbs all the way to 1. F of x is always going to be an increasing function of x. For example, if x prime is greater than x, then f of x at x prime will definitely be greater than or equal to x. Your CDF is going to jump by the amount of which is equal to probability of that discontinuity. That's what this point C is telling you. In addition, your CDF is going to be constant between two discontinuities. So there's always going to be steps which denote the constantness of the CDF between two discontinuity. CDF is particularly useful to evaluate probabilities of those events where we are interested in finding the probability that x belongs to an interval. For example, if I would like to find probability that x belongs to an interval a to b, then I can evaluate that by performing f of x at b minus f of x at a. That is going to give me the probability that x is greater than a but less than or equal to b. Okay, now let's solve a problem based on the CDF. So here we have a CDF, and what we need to do is draw the graph for the CDF, and then we need to reverse engineer and draw the probability mass function using this CDF. In the previous example, I showed you how to derive a CDF chart. In this case, using a PMF, in this case, we need to use the CDF chart to derive a PMF. So first, start with plotting this CDF. So for all the values of x that are less than -1, this CDF is equal to 0. But at x is equal to -1, this CDF jumps to a new value which is equal to 0.2. It remains at 0.2 until the next discontinuity, which is 2, at which time there's another jump to a new value of 0.7, and it remains at 0.7 until the next discontinuity, which is equal to 1. And there's another jump to the final value of the CDF, which is equal to 3. It is indeed a valid CDF because it's an increasing function of x, and there's no dips in the CDF. The CDF starts at 0, goes all the way to 1. It's a valid CDF. Now, to derive the probability mass function using the CDF, all I need to do is look at those points where I have jumps in the CDF. So I have jumps in my CDF here at -1, here at 0, and here at 1. So these will be the points where the probabilities will be equal to non-zero. So probabilities will be non-zero at points -1, 0 at 1, and the probabilities will be 0 otherwise. To find probabilities of these discontinuities, I need to just look into the CDF and find out by how much the CDF is jumping. For example, at x is equal to -1, the CDF is jumping by an amount which is equal to 0.2. So the probability of -1 is equal to 0.2. At 0, the amount of jump in the CDF is 0.5, so probability that x is equal to 0 is 0.5. The amount of jump at x is equal to 1 is 0.3, so probability that x is equal to 1 is 0.3. So that's the probability mass function that I have derived using a CDF. CDF is a useful probability model, but we rarely use it with discrete random variables. The use of CDF is more apparent for very specific random variables, particularly of continuous type, such as Gaussian random variables. So until then, we'll be mostly favoring probability mass functions for discrete random variables and probability density functions for continuous random variables, which you will see in my future lecturettes. Now let's look into some statistics pertaining to random variables, some numbers that describe a data set. One of them is the expected value, which is often referred to as the statistical average. So expected value of a random variable is a probability model, and it tells you what the random variable is expected to take on, what value a random variable is expected to take on for a given experiment. For example, if I were to roll a die, what number can I expect? In physics terms, it is similar to talking about the center of mass. It is the center of mass of your data set. Now, using physics as an example, consider that you have multiple points that are spread in the space. You have points at location x1, x2, x3, and so on until x of 6. So these are the locations of 6 different points. Furthermore, let's say that the probability mass function at these values represents the weights of these different points at x1, x2, x3, and so on. Meaning that probability that x is equal to x1 is the weight of x1, how heavy it is. Probability of x is equal to x2 is similarly the weight of point at x2, and so on. If I would like to calculate the center of mass, I can use my physics principle that center of mass is equal to the summation of product of mass times their location divided by the sum of all masses. Similarly, I can obtain the expected value as summation of product of location times the mass of these objects divided by the individual masses of these objects, and that is going to give me the expected value of x. Notice here that the denominator term is going to simplify to 1 because I'm adding the probability mass function for all the values of x that belong to sample space. That should always add up to 1. So this is the formula that I use to calculate the center of mass or the expected value of a random variable x. So for instance, if I wanted to evaluate the expected value of this random variable denoted by this PMF, all I need to do is summation x times PMF of x for x belonging to the sample space, and the sample space contains x's -1, 0, and 1. So I have -1 times its weight, which is 0.2, plus 0 times its weight, which is 0.5, plus 1 times 0.3, which is its weight. And that gives me the final value as 0.1. So that's the center of mass. It's concentrated near 0.1. So the formula for expected value is x times PMF of x for all the values of x that are in the sample space. It is not uncommon to represent or abbreviate the center of mass or expected value using this term mu of x. The discrete random variables that we have discussed so far, the named distributions, they also have their own respective expected values. For example, expected value of a binomial random variable is n times p. For example, if I were to could toss a coin 10 times, a fair coin 10 times, then the expected number of heads is half times 10, which is 5, meaning that 50-50. I'll get 5 heads, or I can expect to get 5 heads. For Pascal random variable, the expected value is k over p, and for discrete random variable, the expected value is k plus l over 2. Now, I do not expect you to derive these expected value using mathematics for your exams or what have you, but I would like for you guys to use the expected values to calculate the relevant probabilities that are dependent on these expected values. So I may ask you, hey, what is the probability that a random variable x is less than the expected value? So you should be able to know or calculate what the expected value is for a given random variable, which formula to use. Let's apply the principle of expected value for a probability problem. So here I have a packet which is received by a smartphone, and it's going to be error-free with probability 0.95, independent of any other packet. If I were to receive 10 packets, let x be the number of packets received. What is the PMF of x? So which random variable would you use? Pause your video here and try to formulate an answer for part A. Once you're ready, you can unpause and I can show you the answer. Since we are testing 10 packets, which is fixed number of packets, and we are interested in x number of erroneous packets, I'm looking at a binomial random variable, because binomial random variables definition fits into this particular problem. So the PMF of x will be 10 choose x times 0.95. Well, that's the error, and I'm modeling the 0.95 is the probability of being error-free. So probability of error is equal to 0.05. So 0.05 to the x times 0.95 to the 10 minus x, where x can be 0, 1, 2, and so on until 10. So that's the PMF of x. In 1 hour, in part B, in 1 hour, the smartphone receives 12,000 packets. Let x equal the number of packets with errors. What is the expected value of x? So again, it's a binomial random variable because I'm performing or testing n is equal to 12,000 fixed packets, where each packet's testing is a Bernoulli trial. So n is equal to 12,000 and p is equal to 0.05. So the expected value of erroneous packets is 12,000 times 0.05, which should be, I think, 600. So that's the expected value of x. Now moving on, and let's look into some more statistical parameters or some statistical numbers that we can use to explain the underlying data. One of the goals of data analysis is to actually explain the underlying data, to make sense of it, so that your company, your organization can make decisions based off of that. In order to make such inferences, we tend to calculate some statistics, and those are moments and central moments. The nth moment of a random variable x is defined as expected value of x to the n, which is summation x to the n times PMF of x for all the values of x that are in the sample space. So by applying this principle or this formula, we can calculate the nth moment. For example, if n is equal to 2, I am interested in second moment, which is equal to expected value of x squared, which is obtained as summation x squared times PMF of x. So for the PMF problem that I showed you before, where we got the PMF as 0.2 for x is equal to -1, 0.5 for x is equal to 0, and 0.3 for x is equal to 1, expected value of x squared will be -1 squared times 0.2 plus 0 squared times 0.5 plus 1 squared times 0.3, giving me 0.2 plus 0 plus 0.3, which is equal to 0.5. So that was the expected value of x squared for the previous PMF that I had shown you before. That's just an illustration as to how you are going to apply this formula. I can obtain other moments by applying the similar principle. For example, expected value of x cubed is going to give me the third moment, which is equal to summation x cubed times PMF of x. Then comes the concept of central moments. So central moment, specifically the nth central moment, is given by expected value of x minus mu of x to the n, which is equal to summation x minus mu of x to the n times PMF of x, where mu of x is actually your expected value. So you can obtain the second central moment by substituting n as 2. You can obtain the first central moment by substituting n as 1. First central moment is always 0. Now there's something special about central moments. Specifically, when as n is equal to 0, your central moment is actually equal to 0. And it is not difficult to prove this mathematically. Or my apologies, when n is equal to 0, your central moment is equal to 1. Your central moment is going to be equal to 1 because at that point you're just summing up the probability values. When n is equal to 1, your central moment is actually 0. When n is equal to 2, your central moment is actually a very important statistical parameter which we call as the variance. Variance tells you how much the data is spread about the mean. The greater the variance, the greater the spread of the data about the mean. And it gives me a lot of hint with respect to explaining the data. For example, on a given midterm, I may obtain an average marks as 44, but I may get variance equal to 2, which means that most of the students have performed quite closely to the average marks of 44, in which case I'll be happy if 44 is obtained out of 50. However, if for an exam, I have average marks equal to 44 but a variance equal to 10, then that means that there are many other students that have performed either far better or far worse than the average marks. So the variance is going to tell you how the data is spread, and it is going to help you explain the data. In my case, using the example of these marks, it tells me that the latter has much more variance and in student performance, so I need to make sure that I'm able to pull some of the weaker performing students. Whereas in the former case, I'm generally happy that most of the students are performing similarly in the class. When n is equal to 3, your central moment gives you a term which we call as the skewness. Now skewness tells you where the tail of your distribution is, whether it is skewed towards the left side or whether it's skewed towards the right side. The skewness tells you where the data is concentrated, essentially. So these are some of the important statistics that you will come across, which you typically use to explain the data. In fact, in phase 2, I'm going to have you guys use these statistics to perform object recognition. I'm going to have you write the meats and potatoes of an image processing program that can automatically have the computer detect what kind of fruit is present in a given image. It's going to be fun. More on that later. So let's focus a little bit more on variance and standard deviation. So variance is actually your second central moment, and it is obtained as expected value of x minus mu of x squared. It can be simplified as expected value of x squared minus expected value of x whole squared. It's not difficult to prove. I leave that for you guys to prove and apply the mathematical concepts of algebra here to prove that the variance is indeed expected value of x squared minus expected value of x whole squared. Standard deviation is the square root of variance, and to be more precise, is the standard deviation, which is much more useful information regarding the spread of the data versus the variance. Because when you talk about variance, it is in squared units. For example, if I have a data that relates to weights of individuals, then the variance will have a unit weight squared. Now, weight squared, any number which is weight squared, really does not give me a whole lot of insight with respect to how much data is spread. Instead, I will rely on standard deviation, which is denoted by sigma usually in statistics, which is equal to square root of variance. When I take the square root of variance, I get a number which has the same unit as my original random variable. So if my variance is in weight squared units, square root of variance will give me another number, aka the standard deviation, which is going to have units equal to weight. So it has the same units as my underlying random variable, which is the weight of the individuals. So that is much more insightful or it gives me much more insights with respect to how much the data is spread about the mean. So it's the standard deviation which is the more useful information. Together, mean and standard deviation, they give you almost a complete picture of how the data is spread. If you would like to get more insights into your data, then you go on and evaluate the skewness and maybe perhaps the fourth central moment, which we call as the kurtosis. But we are going to discuss about those items in phase 2, when I will actually have you guys evaluate these different terms for performing image processing. The named distributions have their own respective variances. So these are the formulas for the variances of the named distributions. Again, because it's not a mathematics course, we are not going to spend time proving that these are the formulas, but instead we'll be relying on these formulas to find different probability problems. For your midterm, for your exam, I'm going to have you use a cheat sheet. It's going to be an open book, open notes. So all these formulae will be readily available to you. What I'll be interested in is how well you're able to apply these concepts to sciences and engineering problems. I think it's a good time to stop this video lecturette right here. With this lecturette, we come to an end of our discussion on discrete random variables, which is quite useful for most of the engineers, but more useful for computer engineers and computer scientists than not. In my next lecturette, I'm going to start covering continuous random variables, which will be much more useful for civil engineers, for electrical engineers, those people, those engineers that are interested in continuous domain.